Hi, I'm Jamie. What I'm going to talk to you today is about an architecture that we're evaluating here at Capital One. One of the issues that we have right now is testing. In order to ship at the scale that we ship at, we need to have good, fast tests. And I think anybody who, some of the people that work here know that our tests aren't that fast. So my team, has been working on creating an architecture for building features in the app that allows us to write better unit tests, therefore better test times and quicker merges. So I did not come up with the name Reactive Store. Somebody said it and it's stuck. But it is the store pattern that's been, we borrowed it from a few other, it's inspired by a few other patterns that are out in the wild today. So if any of you have ever played the game Katamari Damacy, the goal is that little prince is trying to impress his father by going around the world and collecting things. And I liken that to the state of view controllers in the world today. So some of those things may be networking, some of those things may be analytics, all the different stuff that you have to do. We've got these massive view controllers, and they kind of do this thing here, which is the coolest animation I've ever done. And it gets bigger, and it gets bigger, and then it looks at you and says, test me now. So massive view controller is a problem in iOS, and our view controllers tend to have too many responsibilities. They're super tightly coupled to their dependencies. Obviously they're hard to test because of those two things above it, and they're super fragile. And the fragility comes from sort of not being able to reason about state and state transitions in your view controllers because you have some bool that some developer added to track loading state, and then you have to go add a new feature, and you forgot to flip that bool in your completion block, and now you've got a spinner that stays up that you forgot to turn off. Obviously hard to test because half the time we're just directly instantiating our dependencies inside of our view controller, so we can't mock them out in our test. We're typically pretty tightly coupled to those dependencies, so we, again, by instantiating them in the view controller, then if we want to move away, say like from core data or something like that to some other persistence framework, we have to go do a bunch of refactoring because we've written all of our core data code in view controller. And that's not a knock on core data. That's just a knock on how we build stuff today or or what we're trying to solve here. So I'm not saying the royal we, not pointing fingers at anyone here. We all write really highly testable code, right? So one of the key things that you need in order to write highly unit testable code is to eliminate your dependencies. And the way that you can eliminate those dependencies is by injecting them through like constructor injection or property setting or mocking or things of that nature. So we want to remove any dependencies from code that we want to test because the last thing we want to do is write a unit test and it actually goes out and hits the network and transfers money from bank account 1 to bank account 2 or likes some post on Instagram that you didn't want to like because it was from 3 years ago or something, and that gets weird. Tests exist to verify an output for a given input, so that means that we want to make sure that what we are testing has some sort of output. So we want to think about the code that we write as inputs and outputs. One way to think about this is if you are writing a method and it returns void, then you just wrote that method for the side effects that it's doing, and it's how do you test that code, right? I want to point out that we are standing on the shoulders of giants here. Some of the inspiration is from Flux and Redux, which are some web architectures. We also stole some ideas from Elm, which is a really cool web framework that uses this language called Elm. It looks a lot like Haskell, but it's JavaScript. And then we also have borrowed some patterns from MVVM, and we kind of put them all in a pot and made a stew out of it, and we got Reactive Store. So this is Reactive Store in boxes. You can see at the top, well, first down at the left, we have, sorry, my left, your left, never mind. All right, good, you're laughing. That's what I was trying to get. So down at the bottom there, you can see we have three sorts of types in the system. We have state, action, and side effect. And we'll go over what all of those are, but just know that a store takes in actions and produces states and side effects. Again, we'll talk about what those things are coming up, but I just wanted to point out. So the public API for the store is just one method called dispatch, which takes an action. You can also dispatch an observable that contains the action. We're using RxSwift to make it reactive. You could use sort of any asynchronous communication pattern to do this. We just chose RxSwift because it's highly documented, highly tested, and it's pretty stable. It's been out there for a while. And then the store works in concert with 3 types over to the right. The first one at the top is the action creator. The action creator is responsible for taking in this. You can see the store passes the action creator its state, the current state that the store is tracking, and the action that was just dispatched to it. And the action creator's job is to look at those 2 pieces of information and decide if it needs to go off and do some asynchronous work. And eventually that will produce a new action, which goes straight into the same front door that everybody else goes into. The next thing is middleware. Middleware is just a piece in the system to allow you to watch what's going on, but not actually affect the system or the state in the system. But you can see there's no arrow going back to the store from the middleware. And then the last and probably most important part is the reducer. The reducer takes the current state of the store and the action that was passed in and returns a tuple of state and maybe a side effect. And then we take the result of that reducer and we push the state out on the state observable and the side effect out on the side effect observable if the reducer produced one. By using RxSwift, all of this is reactive, so we don't have to deal with like closures and all these different communication patterns. We've sort of landed on one sort of asynchronous communication pattern using RxSwift. So let's talk about fragility and maintainability, which is kind of one of the big problems that we have in our massive view controllers. Is we go and we are given a feature to write, and we have to add some new behavior to our view controller, and we don't even know where to start. The management, I will read directly from the slide, which you're not supposed to do, but I will, because I'm a poor presenter. The management of a state inside of a system is often intermingled with other responsibilities, and that looks like this. That looks like regular iOS code that we all write, but what's actually happening under the hood is we're dealing with UI events here, right? We have that button tapped method there, and then we're changing some state as well, and that's not locally reasonable. Like I can't follow that. What if I forget to do that somewhere else, or someone else changes that out from under me? So we've mixed sort of in just this one line of code, we've mixed some responsibilities. And with no clear grammar about what's going on inside your system, it's hard to reason about what's actually happening. So we have to use our deductive reasoning skills, which you can be good if you're like Sherlock Holmes, but if you're me, I'm not very good at that. So an example of like no clear grammar is what does should update fields mean? Maybe it meant something when that person wrote that code, but a year later down the line, it doesn't actually mean that. It may mean something else. So we use a reducer to formalize those state transitions. And like I said, a reducer in the Reactive Store pattern is just a pure function, which again makes it really testable, and it has those properties of testability that we want. It takes inputs and produces outputs, and that's how we test those things. So you can see that box to the left or right, depending on your perspective. Okay, sorry, I tried. Takes in state and action and produces state, a tuple of state and side effect. State is the data that we want to track. This is the stuff that we care about. This is the stuff that drives all of our applications that we write. Our job is to manage state. Actions are a way to give meaning to the transitions that we want to affect to our state. And then lastly, the reducers are these pure functions that take those actions and apply it to the state. And the shape of that, again, is this pure function, state and action returning state and potential side effect. So obviously we don't live in a world where we just do everything on device and we don't have to deal with the network or go make calls or get the user's location or any of these other like asynchronous things that happen. So we have to deal with asynchrony, and we want to deal with asynchrony in a way that's testable. So we created this thing called the action creator, which is, again, this is one of those things that comes from some other system that lives out there. Action creators, I think, come from, like it's a plugin to Redux or something like that. So anyway, the idea here is that the action creator's job is to take the current state of the system and an action and decide if it needs to do something and eventually produce an action for the store to consume. Yes, I said all the stuff that now I'm going to show you. Again, sometimes these actions are a result of some asynchronous event that we have to control, and we model that idea, that concept, that responsibility as an action creator using our Swift observables to model that asynchronous communication pattern. Middlewares are like the most boringest part of the entire system because they don't do anything. So I've said throughout this talk, like, hey, testing stuff means that you have to have an output. Well, middleware doesn't. So testing middlewares gets a little weird, but you can certainly do that. So I know that I'm like contradicting myself, but that's okay. Again, middlewares exist to provide capabilities that are plugged into the system but do not affect the state of the system. So you could think of analytics as a potential for middleware. Logging is a potential use case for middleware. And in our implementation, we get two methods in the middleware. These other than the store and the reducer, these are just protocols that you can go and add back onto any types that exist in your system. And the middleware protocol has two methods. One is the pre-execute, which is called before the reducer is applied, and the post-execute, which is called after the reducer is applied. So if you want to do some diffing on your state as it goes through the system, you can certainly do that. Going back, our action creators API is basically is a method called create action, which I didn't put in there because I'm also bad at making slides. But okay, I think I've exhausted all of that. So that's the store, and that's all well and good, and that helps us build a nice, predictable state management system for our application. But how do we get that on screen? So we rely on three other types to drive, to actually get this stuff on the screen. We start with our view controller, which produces streams of user input. So I slide a slider, I tapped a button, and that's it. We don't put any sort of context to those actions. We just expose them as close to the data that UIKit gives us when you tap a button. When you tap a button, you get nothing. When you slide a slider, you get a float. We feed that into what's called an interpreter, and the interpreter's job is to take that raw sort of user input and then apply the grammar of the actions that that user input means to the system, right? So I slide a slider, that means this action. So the interpreter's job is just to map user inputs to actions to run and dispatch them to the store. Then we use what's called a presenter. And the presenter's input is the state coming out of the store, and its output is UI bindings that the view controller can listen to. And then lastly, we have these pesky side effects that we have to deal with, and we use a thing called a wireframe, which is responsible for taking those side effects and realizing them. The thing to note here is, again, with our arrows, you can see that everything sort of has an input and an output other than the wireframe, because we live in an imperative world, and sometimes we just have to do things and let UIKit do that for us, and we can't really control for it. So testing this becomes really easy. If I want to test my interpreter, I just fake user input into it, and then I watch the actions that come out of it and verify that based on the input that I gave the interpreter, the actions it produced were correct. If I want to test my presenter, I can just feed it a bunch of fake states and watch the outputs on the UI binding streams to verify that my mapping of the state to UI is correct. If I want to test the view controller, I have to go do Apple UI. For the store, all of that testing happens on those constituent parts that make up the store. So reducers obviously are easy to test because they're just functions. Action creators become a little bit more difficult. You have to do a little bit more mocking because that's typically where your network calls and stuff are happening. And then middleware, you can do things like recording what is going on in your middleware and verifying that using mocks as well. So going over these new pieces, and the thing to note about this diagram is that this is the MVVM part of the architecture, where the interpreter and the presenter are basically a view model split in half, and that's purely for testability. So dumb view controllers. We want our view controllers to have as little logic in them as possible, because if they live inside the view controller, then you have to create a view controller to test that logic, and we don't want to do that. So we modeled this responsibility as a thing that we call an event provider. And then since that typically is a protocol that the view controller conforms to, then in our tests, we can create these fake event providers to feed into the system. With some notable exceptions, which we talked about, action creators. State mutations are a result of some sort of user interaction. And the view controllers are receiving that user interaction, and then we just expose those interactions in these streams. So, yep, look, see, I'm saying stuff, I'm all over the place. So the next thing is the interpreter. The interpreter's job is to interpret intent. That's why it's called an interpreter. So we map the output of our event provider to actions to dispatch on the store, which we talked about. And then we sort of take so now we're all in this like action world. We can take all of those multiple different streams of UI events. Now we have streams of actions. We can flatten that, merge that down into one stream to feed into our store. And because of the way observables work, it just is magic. They just kind of get interspersed within one another. And we have a consistent sort of like stream of actions going into our store. So this is my example code of what an interpreter looks like. And you can see here, it's literally just calling map. There's nothing special here except for that observable merge, which is the one that's taking those streams and kind of overlaying them together. So it's pretty straightforward. And then you can see here, we have our action there, which is typically, should be, we like them to be enums because it's a better representation of actions, like this could happen or this could happen. I don't want to get into some or product types, but essentially our actions are sum types, not product types. And then presenters, how do we make UI? We do that by transforming the state. We map the output of our store to drive our UI. So you could think this is where your formatters would live, whether you hide views or showing views, et cetera, because I couldn't come up with any more ideas to put on the slide, so I just threw et cetera on there. And this is an example of a presenter. There's a little bit more RxSwift magic happening here, but just know that like we saw earlier in Daniel's talk about the catch and the return, and sort of what's happening here is just dealing with like errors that may happen in those streams. But again, here all you can see is we're basically just mapping the state to UI bindings. And then RxSwift has these really cool bindings that it provides us where we can then drive UI using observables, which is really cool. And then side effects, which is the weirdest thing that like just got added, was like the last thing that we added. We have to deal with the fact that we write code in UIKit, and UIKit is not in this like perfect little little circle of trust. And so what side effects are a way for us to sort of encode those things that we want UIKit to do for us. Show alerts, make UIKit transitions, ask for the user's permissions. We can encode those in a grammar and then pass it to something, and it can act as an interpreter. It can interpret that grammar and do something with it. But when it comes to testing, we can just make sure, we can just look at that data since we're treating everything like data inside the system. And so this is what a simple little wireframe looks like dealing with a side effect. We have one side effect that just says, hey, go show an alert, and that's what's happening here. So we're just using, again, data to drive stuff here. Wow, this went a lot quicker than I thought, probably because I'm nervous. But what about combine, right? Because I've been talking about RxSwift, and I figured that's the big monkey in the room. Wait, elephant in the room? Man, I'm all over the place. Architecture is completely independent. This architecture is completely independent of what library we chose to model our event streams. Obviously, for us here at Capital One, we're not able to use combine right now because of reasons. And so we chose RX Swift. The store can absolutely, this architecture pattern can absolutely 100% be written in Combine because I've done it. But some of the things that Combine is missing, which I just looked at the diffs yesterday, and I think they're adding some of this stuff. RX Swift has this really cool framework called RX Test, and that allows you to create these. I've been talking about faking these streams. We use RX Test to fake those streams and feed them into all the constituent parts of the system, and then we can verify that those streams coming out match the expectations of the streams that we fed it. And then obviously RX Cocoa, Combine has the assign publisher, which is really cool, but there's some really cool UI bindings that RX Cocoa gives us, as well as collection, some stuff for driving collection views and table views with observables as well. And then lastly, Combine requires iOS 13, which is the reason that we can't use Combine. So I flew through that slide deck. I didn't expect it to go that quickly. I'm sorry. So do you have any questions? Oh, yes, question.
Well, I guess there's two. With RX Swift, where are you dealing with the disposables that you generate with the observable?
Great, that's a great question. So disposables, right? So, and this is not just an RX Swift thing, right? Because Combine has cancellables, which is sort of isomorphic, right? So if we go back to this last diagram here, you can see the only thing, it's kind of disingenuous, but the only really subscription that's happening is in the view controller. Everything else is just a map or a transform. There's some stuff happening in the store, but don't worry about that because that's black magic. It's just like a component. So all of the subscriptions and so the disposables that result that come out as a result of that subscription live in the view controller or the thing that's consuming the UI bindings, whatever that may be a view controller, whatever. And then you said you had a second question.
Yeah.
So.
Do you have any instances where you have an observable that you're trying to emit a constant stream of data with, and how do you deal with the error termination? Because once an observable errors out,
Yep.
it terminates.
Yeah, so we deal with that in the store. One of the types I didn't talk about is an error reducer, which you can provide to the store. And anytime anything goes wrong inside of the store, like some observable, like a network recall, like some observable errors out that it may be coming from a network call or something like that, we actually just run this thing called the error reducer, and we pass you the state we were in when it happened and the error that we got, and its job is to return a state and a side effect, and then we can just carry on. As far as errors, otherwise, I'm excited about Combine because if I could use Combine, and when I wrote this using Combine, I made them all nevers, right? So I put none of you can error out, but practically speaking, our view controller, our outputs are what are called control properties and control events. And in RX Swift, they're not guaranteed to not ever error out, but they won't. And then because those won't, the mappings that are happening inside of the interpreter that are producing that action stream won't error out. Inside the store, we deal with that. We actually, because of the error reducer, we deal with that. We make sure that that state stream never errors out. So even though we expose it as an observable, underneath the hood, it's like a relay that can't produce errors. And then again, because our state's not erroring out, our UI bindings don't error out. So we control for it. Unfortunately, we can't control for it like we could and combine with the type system. And we have some plans to maybe even get rid of the error reducer by making our own trait in RX Swift that gives us the behavior that we want from these streams, but but not but we can't, since we can't put the error in the type, we just have to say, well, it's, we promise you it won't error out. John.
What are some examples of things you want to put in the Reactive Store and things that you don't want to put in the Reactive Store? If I'm creating an application that is loading and then shows something. All of it going in Reactive Store for all eternity?
So the question is, what goes in your state? State, right? Because the store is just at its root level, the store is just an engine for running the reducer. I tend to push people towards if you can, how do I say this? If you can determine. Wait, how do I usually say this, and now I can't remember it because I'm on stage and I'm nervous. So, if it's a source of truth, if you can derive, thank you, that's it. You remember from my talk. If you can derive the piece of information from something else, then it doesn't belong in the state, because you can, use other properties of the state to derive that value. Exactly. That should like a formatted string of your account balance shouldn't be in the state. Just the double itself should be in the state. Redux, the Redux pattern basically says your entire application data lives in the state. I don't think that's necessarily practical for like a large team that's shipping features across multiple organizations, and that would be just a roadblock. So we've gone down the path of which is the more flux way of you have a store per feature. So that's kind of where we're headed. Does it?
Can you add and remove those feature states? Or are they just like as you add them, as your user goes farther and farther, you load like the state object massive?
No. Basically, you get like a store per feature. So each feature is responsible for its own data.
So I couldn't go out and access accidentally another piece of state?
Just as much as you could in current, just as much as you could in current apps. What we do encourage, though, is that your states are structs that are immutable. So, like, even if you have it, you can't do anything with it. Daniel, yes.
Your stores are essentially single system?
Well, yeah. We don't say have like store.shared or something like that. You instantiate them, and then something holds on to a reference to it. The way that we're doing it is we have like a host view controller that acts as like our model, our memory management model. So like the store lives in like on a view controller, and then it just goes away with the view controller.
This might be an unfair question because you like your talk, but as you anticipate SwiftUI and controllers going away, this seems to be ready for that.
Right.
This seems to be set up. So what would change if you implement our?
I don't know. I haven't had time to think about that. And it's a great question. And it's definitely something that's on my radar and my team's radar going forward. Like, how can we make this work with SwiftUI or something like that? But I don't know. And I think that this is kind of like sort of in the spirit of what Apple's trying to do with Combine and SwiftUI. Maybe not like the same names, but like the concepts seem to be the same. At least, if you look at it kind of far away. Yes, question. Yes, if you work Capital One. Yeah, okay, yeah, we can talk about that. He was asking if there's a repo, and I said, yeah, if you work Capital One. Any other questions? Cool. I'm going to give you back all like 17 extra minutes because I talked really fast and didn't have a lot of content for my slides, so I'm sorry about that. But if you want to, where are we? Go, 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 go. If you want to, ask me anything outside of this, I'll be around. My Twitter handle is my name. Feel free to follow me on Twitter, but I mostly post about like baseball and, well, baseball. So, no, Red Sox. Let's make that very clear. I'm a Red Sox fan. Anyway, what's that? What was that? Yeah, that's okay. It's tough being one of the best teams in the game. So. All right, great.